Thank you. Welcome to DVCon again, once again. On the track 1 paper presentation, separate individual track that we have, track 1, track 2, track 3. And yesterday also we had a few paper presentation. And today also we have 4 more papers that is in the track 1, similarly in other tracks as well. So please try to utilize your time frame whenever you have switched between the tracks, and also poll your results or your feedbacks in your in the screen which is presented in the Q&A session. Okay, so just want to start immediately because as we are running out of 5 minutes, and it's fine, and we'll start with the new paper presentation, especially from the track 1, and the topic is Goal UVM Scoreboard Basics and Beyond. And this is something different topic name which I see, because it says it's a goal point of view, and the author is coming from Siemens, and the name is Rich. So welcoming Richard to present the paper Goal UVM Scoreboard Basics and Beyond. Thank you.
Hi, my name's Rich Edelman and I work for Siemens EDA. Today we're going to talk about the UVM and scoreboards. Today's paper is Goal, UVM Scoreboard Basics and Beyond. Hopefully after today you can get started using the UVM to do some scoreboards yourself. Well, what's verification? Really, it's checking the results. You could call it a checker, a golden model, a scoreboard. In the old days, we'd have a file full of inputs and expected outputs, and we'd feed those into a test bench. And those inputs would go over to the device under test, and then some outputs would come out, and this checker would check those outputs against the expected outputs, and we'd get a pass-fail. Well, really, it's the same thing for the UVM. The UVM has this scoreboard. It's going to do the checking, and in this case, there's 2 environments that are connected to the device under test. There's some input and some output, and we're going to do some checking, and we're going to send a transaction over this connection here to the scoreboard, and the connection is generated by a monitor. And this monitor, in this case, is sitting on this bus, and this monitor is sitting on that bus, and we're going to do some checking in the scoreboard. So what's a monitor? It just needs to monitor something. Connect it to a bus and report transactions, sample a process, make a report, text file, log file. Anyways, a UVM monitor is usually drawn like this. It's a box. It's got this analysis port where information comes out, and it's connected to a bus probably. In system Verilog syntax, we declare a monitor extends a UVM monitor. It has a class member variable called T. It's a transaction. That's what we're sending around. We're sending around a transaction. It has an analysis port that's built to carry a transaction, and it has a bus. So those are the class member variables that the monitor has: a bus, an analysis port, and a transaction handler. There's the constructor for the monitor, and then the build phase. This is where we're going to build out the analysis port. This is all straight UVM so far. In the run phase, we're going to have a thread that runs forever. It's waiting on the clock, and it's waiting for ready and valid on the bus to both be 1. When that happens, we're going to call that a transaction. That's the way we're building this monitor. That's a transaction. So we're going to create a transaction. We're going to construct it. And then we're going to pick some interesting things off the bus. We're going to pick the read-write signal, the address. We're going to pick the write data or the read data. And we're going to put that into a data array of bytes. In this case, we just need 1 byte. And we're going to copy the ID. And then we're going to send this out, the analysis port, with ap.write. This will publish the transaction to subscribers. That's a publisher-subscriber paradigm. So that's the whole monitor. So what is ap.write? Well, you can see it's very simple. When that function write is called, what the UVM does is it goes through any of the connections, and those connections are called analysis exports. So this is an analysis port, and the connections on the other side are called analysis exports. That's what the write routine is going to do. It's going to call the write routine on the other side. So the write routine on the analysis port will call the write routines that are connected to any analysis port, analysis exports. So here's an analysis export object that's somewhere. it's at a hex address. And then here's another analysis export object that's at a hex address. And they have implemented a write routine in them. So when ap.write gets called, it will go find these objects and call those write routines. And that's how the transaction gets over there. As a bonus question, you can use as homework, why is the write routine a function and not a task? So publisher subscriber, this is how we're communicating. Here's some publishers and subscribers down on the bottom. The publisher publishes a value to a list of subscribers, possibly empty. A subscriber receives the published value by implementing a write routine. In this case on the left, there's one publisher and there's one subscriber. Here, there's a publisher and 2 subscribers. And finally, there's a publisher and 4 subscribers. Analysis ports publish and analysis exports subscribe. You didn't know there was anything funny in the UVM, but this is a very funny joke. What's the difference between an analysis port and an analysis export? Not much. So there's a couple letters, the export and the export, and then there's a definition in here, export and a 1. That is just comedy gold. Okay, back to our test bench. So in our test bench, we probably have a transaction. That's the RW, address, data, ID, class member variables, and a couple of functions, a very simple transaction. And that's in our existing test bench, and we're going to add this scoreboard in. So we're going to need a comparator because we want to compare 2 transactions. So the comparator is built to take an object in, and what we're going to do, it's the right-hand side of a comparison, you might say, and we're going to use a little polymorphism here, and we're going to do a cast to a transaction handle so that we can have all of those class member variables available to us. So this cast will succeed because we're passing in transactions. That's what we're dealing with. And then once we are in here, we're checking the attributes. If anything does not match, we're going to return a 0. It's a fail. It doesn't match. So if ID doesn't match, if RW doesn't match, if address doesn't match, we're going to fail. We're going to check the size of the array and the elements of the array. And if they do not fail, so if that means they matched, so everybody matched, then we return 1. Pretty easy to write a compare routine. Okay, an in-order scoreboard. We're going to start with the definition, how we write the code. We're going to use a couple of macros in the beginning. And yes, macros. We'll have more on those in a minute. We declare our scoreboard class. It's just a UVM component, and it's got a couple of analysis exports. So we're declaring the scoreboard. It's the subscriber. So it's analysis exports, and this is oddly declared syntax, and it says here, no questions. So these are analysis exports we're going to connect to. We also need a couple of FIFOs to hold the data. Expected data is coming in and actual data is coming in. These are the transactions. We probably don't need a FIFO. In this case, it's a really simple scoreboard, but we're going to use a FIFO because it's just really easy to manage. We can push things onto the FIFO and not worry about them. And the constructor for the scoreboard is simple as well. In the build phase, we're going to build out the 2 FIFOs and we're going to build out the 2 analysis exports. Nothing magical there. Now the magic comes in the write routine. So these write routines that we're implementing are leveraging those macros that we talked about in the beginning. So we have 2 write routines, not just write. It's write expected and write actual. And those macros help map the analysis export writes into these writes. But it is magic, and it just doesn't matter. You connect to those analysis exports, and then the expected analysis export will cause the write expected to be called. So the write is calling this routine for the expected analysis export. That transaction that's sent in, we just put it in our FIFO with a try put and return. So the idea is these write routines gather the information, they put them in a data structure, and then they return. So further processing can continue. So what happens in the run phase is sitting there and it's in an infinite loop and it's waiting for those FIFOs to get some data. So the write routines are putting things into the FIFO and the run phase is getting them out. So the run phase is going to execute this line, expected FIFO.get, and that is going to block until there's something in the FIFO. And when an expected value comes in, then that will return, and then actual FIFO will get called. That'll block until it has data. And then now, once that gets passed, we have two transactions. We do transaction.compare, and we give the other transaction. If it's a match or a mismatch. So it's really a simple routine, getting the information out of the FIFO and doing a compare. There's some debug aids in here to help us do debug. It's also the transactions that come out of those FIFOs. You can put these variables, these class member variables, in the wave window and have a look at them. You need to do a little debug. Then finally, in the in-order scoreboard, we need to check at the end. So at the end of the UVM phasing, there's a phase called check that's going to get called. What we're going to do is we're going to see, is there anything left in the FIFOs? So if there's anything left in the FIFOs, that means we got stuck and didn't get all of the transactions that we wanted. So that's an error. So if the size is not 0, it's an error. All right, back to those macros. So here's us using the macro on the first line, and here's us expanding the macro. This is the expanded macro of UVM analysis imp decal with the argument underscore expected. So underscore expected, it's creating a class. It has some mumbo jumbo in here, all this boilerplate. And then this is the part that we really care about. So it implements a write routine. Well, that's exactly what a subscriber should do. So this analysis export, this implementation of an analysis export is implementing a write routine. It's taking a transaction in, it's parameterized to the right thing because we're going to declare this in that declaration which was no questions, please. We're going to declare it with a transaction handle. And anyways, it's going to do m underscore imp dot write expected. And m underscore imp is the implementation that we passed in. So it's going to do scoreboard dot write expected, which is exactly what we want. So this is a don't ask kind of situation. Just use the macro and be very happy. What about the out of order scoreboard? So in order, we expect them to come in 1, 2, 3, 4, and they do 1, 2, 3, 4. It's pretty easy. In an out of order scoreboard, well, what we expect is eventually we're going to see 1, 2, 3, 4 eventually. And actually, the way the order happens maybe is some other order, 2, 4, 3, 1, let's say. So it's a little different. We're going to declare our scoreboard here, the out of order scoreboard. And again, there's a couple of analysis exports. So we have analysis exports that take a transaction and are going to call it into the scoreboard out of order model. We have now, instead of FIFOs, we're not going to use FIFOs for storage. We are going to use an associative array. So out of order means we might have to save the first value that comes in on expected. We might have to save that until the end of simulation because that actual might not show up until the end of simulation. So how do we match up these pairs? We're going to use an ID field in each transaction. So the transactions will have an ID field, and that ID field will be used as an index into the associative array. So when ID number 1 comes in for the expected, we'll put it in the first array element. And then finally, when the actual comes in that has ID number 1, we'll put it into its array, and then of course we'll do the matching. So this is going to allow us to do the expected coming in, expecting 1, 2, 3, 4, and we're going to be able to match these up by index. The 2s will go together, the 4s will go together, the 1s and the 3. In the build phase, we just need to build out the analysis exports, really easy stuff. Okay, the write routines for out of order are a little more complicated. We have some debug aids again. These are the handles. These are the transactions that come through the write routine. So in this case, we're going to assign that variable just so that we can have a class member variable that has that value. Now we can see it in the wave window very easily. And then we have, we'll skip to this third thing. We have the value going into the array. So here we're filling the expected array value indexed by the ID with the class handles. The class handle is going into that index. And then we're telling our checker, we're telling our run phase, hey, something changed. What we're going to do is we're assigning the ID that changed. And so that ID changed, and now the run phase, we'll see in a minute, can trigger on that and go check to see, in this case, so we just got an expected. The run phase needs to go see, okay, we got an expected. Is there an actual? If there is, then we can do some checking. And then the actual write routine is implemented exactly in the same way. So what does the run phase do in out of order? Well, the run phase is very simple. It forks two threads that run forever. They wait for something to change. When something changes, they call this routine. When the routine returns, they go and wait again. So that's what they do. They wait for something to change, and then they pass in the thing that changed to the check routine, the check routine. What does the check routine do? Well, it has a couple of handles that it's using. And the check routine of a certain ID says, well, do they both exist? Is there an actual element and an expected element? Oh, there is. Then we're going to do a check. So we're going to grab the expected one and grab the actual one out of their relative arrays, their specific arrays, and then we're going to do the compare. So we do transaction.compare against a transaction. It's either going to match or not match. That's that compare routine that we implemented earlier. And then, of course, we clean up our array. So we want to get rid of the things that we just checked. They're gone. We have that same check phase at the end, and this is the same thing. We have expected arrays. Is there anything left in our associative arrays? If there is, it's an error. All right, now we're going to build our monitors into our environment. So we declare a monitor, we construct our monitor, and we connect it. So this is how we connect an environment that we saw in that first slide to a bus. We were going to just assign it. We assign the bus to the monitor, just like we assigned it to the driver. Up in the test, we're going to need to build our scoreboards. So the test has a scoreboard in it. In this case, we have two scoreboards, mostly just for the paper. We have two scoreboards. We have the regular scoreboard and the out of order scoreboard. In that environment, we do the connection. This is probably the trickiest part. So we have our analysis port that's in our monitor. The analysis port is publishing data to analysis exports. And so these analysis exports, you could think about them, they need to go on the list. The AP has the list, so we're adding this analysis export to the list, we're adding that analysis export to the list, and so forth. So this is where we connect things up. We connect up the monitors that are in the environment, their analysis port, with the scoreboard's analysis exports. So we get all these things connected up and built, and we run our test, we run our simulation, and we can show the transactions that we're going across the bus and color them. We can have our in order monitor show up here, the class handles that are in the in order monitor. We can see the actual bus. We can show the in order scoreboard and its class member variables. These are the transaction handles that came through. We can show our out of order monitor with the bus. We can also have the out of order scoreboard. It's a little more complicated. It has a couple more data structures. You can see all of the arrays and when things change. So in conclusion, the in order scoreboard that I've shown is 153 words, and it is quite generic. You'll be able to use it almost as is. You'll need to change it a little bit, and of course you'll need to implement your own compare routine and a few other things. The out of order scoreboard is a little more complicated. It has a few more data structures, but same thing. you can almost use it as is. It uses UVM standard connectivity. There's many, many different ways to do connectivity in the UVM. This is I would say the standard way, or one of the easier ways with analysis exports and analysis ports. It's very simple to write a compare routine. You don't have to compare every field. And it's really easy to add it to any test bench. So we had this existing test bench. We added a monitor here, and this scoreboard. Thank you very much for listening. Please contact me at rich.edelman@siemens.com if you would like to have the source code. Thank you very much.
Thank you, Rich. It was a wonderful presentation. I think it's not like a paper presentation; it's more like a tutorial. That's what we see. I think you bring back all our old, the initial way of UVM test bench that we have normally bring up. I think in the benefit of time, maybe I'll just wrap up with small question from my side, and especially on how do you see, okay, I understand the analysis port and analysis export point of view and so on. But I think as you talked about FIFO, right? I think you have FIFO's point of view. Is there anything specifically that you also consider the latest UVM 2.0 or the TLM perspective also, because a lot of people using generic payload for the scoreboard also mechanism as you're talking about the transaction ID?
Yeah, sure. Absolutely. You could use generic payload. I mean, there's no magic in the way that I showed connecting. There's also no magic in how you pass the data. So a generic payload is a bunch of data that you're going to pass over like a transaction. So yeah, absolutely can use that, and that you can leverage that into things like UVM Connect and over on the System C side too. Yeah.
Yes. Okay. So on top of the other question, like especially how do you take care, especially on the different kind of interfaces? It is only specific to certain interface that you are looking as an outer of order, or it can be helpful for any other interfaces?
Yeah, I guess the idea of out of order a checker is just to show that, well, sometimes the checking is a little more complicated, and you have to put a little bit of an algorithm in there to match things up. The out of order thing I showed was pretty simple. You could imagine that there's other transactions that get split up, and you have to actually coalesce them together in order to figure out what's going on to do the comparison. So yeah, different interfaces will have different kinds of scoreboards. Yep.
Thank you. Thanks, Rich. So I think that's a few questions from our side. Thank you once again for your wonderful presentation, especially as like a tutorial point of view. Hope people will contact you, especially to get the source code.
Yeah, well, thank you for having me.
Thanks, Rich.
Yep.